Yes, Hamna, can you hear me now?
Yes, ma'am.
Okay, so I'm starting the chapter circles, which is remaining. And I think one more chapter is remaining. What is that? Surface area and volume we have done, Arsha. There was one more. Just let me just check. Probability we have done, statistics we have done. I think areas related to circles. No, we have just done it. Construction circle was remaining. Statistics. Okay. Yeah, okay. Statistics is remaining. Okay, yeah, I remember. Okay, anyway, after this we will do. Okay, circles. Uh, First of all, there are two terms you need to understand about the circle. Okay, before that, let me take three situations, right? I have one circle. And then I have one circle and one line. So there can be three situations. Either the line is passing through the circle, right? Or the line is just touching the circle, or they are separate from each other. Is that clear? This is the line L and this is circle. So as you can see in the case 1, the line is intersecting the circle at 2 points, right? So this line in this case is called a secant. Right now in second, the line is just touching the circle. So it is touching only at one point. See, it's difficult. You might think that there can be, many points where it is touching. No, because it's difficult to draw in such a small figure. But if you magnify it and see, so it will touch only at one point. Is that clear? So there's only one point which is common to the circle and this line. In this case, this line becomes a tangent to a circle. And third case, there is no name for it. They are separate. Line and circle, they are separate from each other. Is that clear? So first thing is just define a secant and then you define a tangent. Okay. Sorry. Secant. So a line um, which intersects the circle in two distinct points. Is called a secant. Secant to a circle. So please don't write only secant. There is no meaning of it, right? Secant to a circle. Write like this. Tangent to a circle. Secant to a circle. So make it a habit. And yeah, you can draw a picture. So there's a circle and then there's a line which is intersecting it at 2 points. So this is a secant, right? To a circle. Then you have a tangent. Now please define it. So a tangent to a circle is a line which intersects the circle in exactly one point. So exactly one, right? Distinct, two distinct. They are different from each other. So you have a circle and then choose any point, and this is a point P. So this will be called a tangent. Now this point P, as you can see, this is a common point, right? This point P is a part of circle also. This point P is part of the, if I just give it some name, AB, line AB also, right? So this point P is called the point of contact. Point of contact, I mean the point where the tangent is touching the circle or intersecting the circle at only uh, one point. Fine. Now let us discuss some properties of tangent. Sorry, tangent to a circle. So the first property, which is actually a theorem, theorem 1 you can call it. So please write, then I'll explain. So a tangent to a circle is perpendicular perpendicular to the radius through the point of contact. So earlier also this theorem came in CBSE exam to prove. I mean many times, 5-6 times it has already come, and it's very easy. Okay, now understand this. Okay, now don't write. Okay, please understand. So a tangent to a circle is perpendicular to the radius through the point of contact. So that means if you have a circle and this is, let's say, the point of contact. So at this point of contact, if you draw a circle, sorry, a tangent, and you drop a radius. So at this point, the tangent will be perpendicular to the radius. Is that clear?
Yes.
Okay. Let us prove it. So if I draw a proper figure for it, you have a circle and let's say we have a tangent here. So this is the center of the circle. Let me call the point of contact as P and let me give it some name, AB. This is a line, okay, line AB, which is a tangent to a circle. Join this OP. So what is given to me? A circle. Uh, or you can call it like this also, a circle COR. So this is how we represent a circle. That means O is the center of the circle and R is the length of the radius. Is that clear? Okay. So a circle is given and a tangent is given and a tangent. AB at point P. So you have to prove that they both are perpendicular to each other. So to prove that OP is perpendicular on AB. Okay, now please don't write. Now listen to me one thing. Um, for example, I have a point here And then I have any line. Let's say this is my line L, this is my point P. Now I want to find the distance between this point P and this line L. So how should I place my scale?
Perpendicular.
Exactly. So uh, when we want to measure the distance between the point P and the length L, so we take the shortest distance possible. Is that clear? So the shortest distance possible is, it is the perpendicular. So the perpendicular distance is the one which is the shortest distance possible. Is that clear? So I can place my scale like this also. I can place my scale like this also. So you can see they all are different lengths, isn't it? So with which length will I choose? So when we want to find the distance between the two things, so we always take the shortest length between them. Is that clear?
Yes, ma'am.
And the shortest length is the one which is perpendicular on it. I hope it's clear to everyone. So this concept we are going to use here in this theorem. Okay, so you do one construction before it. Take any point. I take any point Q, let's say. You can take it very close also, no issue. And then join it, OQ. And this point, I am giving it some name. Let me give it R. So I think you should write the concept which we are using. So we know that among all the segments or line segments, among all the line segments, joining joining the point O or center O to a point on AB, am I audible? Sorry, I lost my connection. Yes, can you hear me?
Ma'am, my voice is breaking.
Yes, Hamna, am I audible now? Rida,
Yes,
Harsha.
ma'am.
Okay, sorry, I lost my connection. So, anyway, I was saying that we know that among all the line segments joining the point O to a point on AB, right? I can take any point on AB and I join it with O. So, I can have so many lines. Now, among all those lines, the shortest one is perpendicular to AB. We know this. Is that clear? Right?
Yes, ma'am.
So if I want to show that OP is perpendicular on AB, right? Ultimately, I want to show this thing that OP is perpendicular to AB. So it is sufficient to show that OP is the shortest length between O and P. So I'm going to use this concept. So I'm going to show that OP is the shortest length, the shortest segment between O and the tangent. Is that clear? Okay. So you can further write it. So to prove that OP is perpendicular to AB, so it is sufficient to show that OP is shorter than any other segment joining O to any point on AB. Right? So I have taken any point on AB, which is my Q point, right? I have taken some other point, which is Q. So I want to show that OP is smaller than OQ. So obviously I cannot take infinite points. I'll show for only one point, which is possible for any other point also. Is that clear? So let us do it. Now in this figure, what you can see is, can I say OP is equal to OR? Why I can say? Because both are radius, right? You can call it some equation number 1. Now also my line OQ. So I can break it into two parts. I can write it OR plus RQ, isn't it? Right? OQ can be written as OR plus RQ. So what is the meaning of it? So this implies that your line OQ is greater than OR, right? I mean, you have to add something to OR, then it is becoming OQ. So that means it is greater than OR. Okay. Now I can replace this OR by OP from 1. Is that clear? So I have shown that OP is smaller, or you can reverse it. So this implies that OP is smaller than OQ. So if I take any other point, which is Q, and you join it with O, so it will always be greater than O, or OP is smaller than OQ. So thus, we have shown that OP is shorter than any other segment joining O to any point on AB. So when this is shorter, I mean, it will always be shorter. So this is the shortest length. Now, what does it imply? So therefore, we can say that OP is perpendicular on OQ. No, sorry, AB, not OQ. Any problem, anyone? Rida, any problem? See, Rida, you have to unmute yourself, right? Please say yes or no at least. Harsha, any problem?
No, ma'am.
Hamna, any problem here?
No, ma'am.
Okay, fine. Now, please write the converse of this theorem also. Converse of theorem 1. So, now in the converse, what will be given? So, it is already given that the angle is 90 degree and you have to show that it is a tangent. Understand? So, in the theorem, what was given? There was a radius which is given and there was a tangent which is given, right? And we have shown that the angle between them is 90 degree. Is that clear? Now in the converse, obviously there is radius and the angle is already 90 degree and therefore it will be a tangent. Is that clear?
Yes, ma'am.
Okay. So just write down a line through the end point of a radius, and perpendicular to it is a tangent to the circle.
How to prove this one?
Yeah, so we will prove it also. This small proof. Okay, so this time what is happening? You have a circle and this is the radius O and P, right? And there's a line here. So I'm not calling it a tangent. It's a line I'm calling. So it's a line. Again, I'm calling it AB to keep it similar. And this is the point P. So now in this case, it is given that a circle C whose center is O and radius length of the radius is R. Okay. And a line. So please note a line, right? A B or A P B, you can say. Uh, which is perpendicular. So this is already given that it is perpendicular. Perpendicular to OP, right? So this is given now. Now this time you have to prove that AB is a tangent. Please join it. And same way, we will take any other point here. Let's take Q and then you join it. And this point I'm calling R. So I have to show that AB is a tangent, right? This angle is already 90 degree given to me. Mm. So similarly, take any point Q other than P. Start like this. Take any point Q on AB. Obviously other than P, and then join OQ. Now, what is given to me? So the first thing is given that OP is perpendicular on AB. This is given, right? Now, when it is already perpendicular, so that means it is the shortest line segment possible. Yeah.
Yes, ma'am.
Okay, so that means it is the shortest segment among all the segments which are joining O and the line AB. So this implies among all the line segments joining O to a point on AB, OP is the shortest. Right, Hamna? So,
Yes, ma'am.
okay, the perpendicular means that this is the shortest length possible. Okay, so I can write it when this is the shortest length. So I can say OP is smaller than OQ, right? Sorry, OQ. Or just flip it. I can say that OQ is greater than OP, right? Now, when OQ is greater than OP, so I can say that the point Q lies outside the circle. See, OP is what? OP is radius. When some length is greater than radius, so obviously it is falling outside the circle.
Yes,
Yeah.
ma'am.
Or you can add one more step if you want, right? You can break it like this, that it is OR plus RQ. I mean, you can call it like this if you want to write, otherwise there's no need. So that means OR is radius, as you know. So, and then you are adding something. So obviously it is going outside the circle, right? You can skip it or you can write it. It's your choice. So it means that Q lies outside the circle. So we can say that, I mean, every point on AB which other than P, right? It is going to fall outside the circle, isn't it? So the meaning is that the AP is meeting the circle only at point P, right? And therefore AB is the tangent at P. Understand? Just give it some words, write it. Thus, every point on AB. So this is possible for every point. We have shown it only for one point Q. You can take any point, same thing will come. So thus every point on AB, which is other than P, uh, yeah, so every point on AB other than P lies outside the circle. Understand? Okay. So this shows that uh, this shows that AB meets the circle only at point P. Is that clear?
Yes, ma'am.
Okay, and thus we can say that AB is a tangent at point P, is a tangent to the circle at point P. So we have shown that AB is a tangent. Okay, let us quickly do exercise 10.1 of NCRT. 1 minute.
Ma'am, can you show the last sentence?
Yeah, sure.
Okay, ma'am. Thank you.
All right. Now see here. First question. How many tangents can a circle have? Yeah. Any answer?
Infinite.
Yes, obviously infinite, right? So there can be infinite points on a circle. So every point can have its own tangent, right? So like that, you can have infinite points, tangents, infinitely many, you can say. Infinitely many tangents. Now, second question, fill in the blanks. A tangent to a circle intersect it in how many points?
1 point.
1 point. Second, a line intersecting a circle in 2 points is called a
Secant to the circle.
secant to the circle. Good. Where's my pen? Okay. Yeah. Okay. Secant to a circle you can complete. Third, a circle can have dash parallel tangents at the most. Okay, so how many parallel tangents it can have? Now try to understand. Two, yeah, obviously two. Why two? Um, so we have learned that a tangent is perpendicular to the circle, right? So if I draw any tangent here, so that means this angle is 90 degree. So if I want to draw something parallel to this line, so it will be like at the opposite end of the diameter. Is there any other possibility? Because this angle has to remain 90 degree, right? This we know. Between radius and tangent, the angle is 90 degree. So if I'm taking here, then I have to take exactly at the other end of the diameter, right? Or if I'm taking here and let's say this is the center, so I have to take at the other end of the diameter, then only this angle will be 90 and this angle will be 90. So at most I can have only two parallel tangents. Clear? Okay, so two. The common point of a tangent to a circle and the circle is called point of contact. Yes, I told you. So this point, as you can see, this point P is part of this line also. Now this point P is part of the circle also. So this is a common point, right? This is called the point of contact. Okay, second question now. Now see here, a tangent PQ at a point P of a circle of radius 5 centimeter. So you have a circle whose center is O and there's a point P. Let's say this is your point P. The radius is 5 centimeter. The tangent PQ. So this is something like this. So there's any point Q, let's say here. At point P, okay, meets a line through the center O at a point Q, okay, so that OQ is 12 centimeter. This is 12 centimeter. The length PQ is, you have to find this length. How will you find it?
Pythagoras theorem.
Why can I use Pythagoras theorem?
Ma'am, because OPQ would be 90 degrees.
Exactly. So we will use the theorem that the tangent is perpendicular to the radius or the radius is perpendicular to the tangent. And therefore it is a right angled triangle, right? So please write it as the tangent at P, sorry, tangent to a circle at point P is perpendicular to OP, right? So therefore we can say that the triangle OPQ is a right angled triangle. And now we can use Pythagoras theorem. Now quickly tell me how much is PQ.
Ma'am, under root 119.
Okay, under root 119. Yeah, that's right. Yes, I'm now okay. Now fourth question, you can see. So draw a circle and two lines. Okay, so you have to draw a circle and two lines parallel to a given line. Okay, so there's a given line, let's say This is a given line. Let me call it AB. This is your given line. So to this given line, you have to draw two parallel lines, two lines which are parallel and a circle, okay? Such that one is a tangent and the other is a secant to the circle. Okay, first you draw like any two parallel lines, right? Let's say this is the line C and D, and this is the line any EF, you can say. So I have drawn like this, that AB is perpendicular to CD and A is also perpendicular to EF, right? Okay. Now one line has to be a tangent and the other a secant. Mm, So no issues. I mean, you draw a circle like this so that, I mean, your one line becomes a tangent and the other becomes a secant. Any problem? You can also pass this to O. There's no issue.
Ma'am, can the diameter also be considered as a secant?
Yes, it is the longest secant possible because it is satisfying the definition that it is intersecting the circle at 2 points. No, actually, see, diameter uh, and a secant, there's a difference. You know, diameter starts from here and it ends here, right, Harsha? And secant is a line which actually passes through it. Understand?
Okay.
So diameter, you can say, is a part of secant if it is passing through the center. So diameter cannot, pass through the circle. Okay. Hamna, is that clear? Okay, now after this, uh, let us discuss another topic, that how many number of tangents to a circle. Um, from a point, right? I mean, I have a point and I want to see how many tangents I can draw to a circle. Now there can be three cases. So I'm drawing three circles. Sorry, they don't look like a circle, but please take them as circles. Okay. So now there can be three possibilities, that my point P is inside the circle, right? Now my point P lies on a circle and the point P is outside the circle. Clear? Okay. Now, if the point P is inside the circle, I want to draw tangents. How many tangents can I draw? Zero, because any line which will pass through point, it will become a secant, right? It will not become a tangent. Understand? So no tangent possible here. No tangent can be drawn. Now, if the point P lies on a circle, so how many? Like you draw a line which
Infinite
pass.
one.
No, not infinite, only one, isn't it?
Okay.
You have a single point P. How many tangents you can draw? Only one?
Yes.
And this is the definition of the tangent, that it touches the circle only at one point, right? So one tangent can be drawn if the point is lies on the circle. If the point is outside, now how many tangents can I draw from this point? So I can draw two tangents. How? I mean, if I draw a line like this, which pass through the point and it is touching at this point, right? Then another line I can draw like this. So this is another tangent possible. So a point which is outside the circle, two tangents can be drawn. Is there any other possibility? See, understand it like this. You have a circle here, right? And then you have any point P. Now, from this point P, infinite lines can pass, isn't it? Yeah, this you know. From a single point P, infinite lines can cross this point. So there are only 2 points. There are only two lines which will satisfy this condition that if you extend them, I mean, it's going to touch here. Another line is going like this. Next line is going like this. So there is only one line possible which will actually touch the circle, right? And similarly, there can be one more line which will exactly touch it. Otherwise, all the lines are not going to touch the circle. Either they will go away from the circle or they will, intersect the circle. So they will not become tangent. Is that clear? Is that understood? Harsha, any confusion here?
No.
Okay. So two tangents can be drawn from a point which is outside the circle. So you can just summarize, right? Or you can call it note. First, uh, no tangent can be drawn to a circle from a point lying inside it. Is that clear? Okay. Now, second, when the point lies on the circle, so one and only one. One and only one. Okay, there's no other possibility. Only one tangent can be drawn to a circle at a point on the circle. Third, two tangents can be drawn to a circle from a point lying outside it. Is that clear?
Yes.
Okay. Now, what is the length of?
Can you show the last point?
Yeah, sure.
Okay, ma'am. Thank you.
See how to measure the length of a tangent. Obviously, if you look at this figure and there's a tangent, and obviously we draw it like this, right? So that means this line is going up to infinity on both the side. It's a line. So how will you measure its length, right? So to measure the length, I mean, we don't measure the length of this whole line. What we measure is we mark the point of contact, which is P, and then we take any other point. For example, I have any point here, right? So I can measure the length from this point of contact up to this point. Let me call it Q. So this PQ will be called as the length of the tangent. Obviously, it's also a tangent which is passing through P. Sorry, then I think this I should not draw, otherwise it will become, contradictory. So I'm saying only one tangent can pass from a point P, right? I hope it's clear. So
Yes,
this length PQ will be called as the length of the tangent. So you don't have to write it, just try to understand. So there's a theorem about the length of the circle tangent now. You write it. And this many times, I think many times it has come in the exam, so it can come. So the theorem is the length of two tangents drawn from an external point to a circle are equal. Right? So I'm trying to show that, for example, I have a circle here. Say this is my circle. It's looking like an egg, isn't it? Sorry. Okay, better. So it's my circle. This is the center O. So you take any point outside it. I'm taking a point here, and then draw two tangents. So from this point, I'm drawing a tangent here, and then I'm drawing a tangent here. Give it some name. Let me call them PQ. Now if I draw the radius, so I know they are perpendicular, right? This is the radius. Then this is center O. You can also join this. So basically I have to show that AP is equal to AQ, right? The length of the tangent is equal. Now this is very simple. If I show that these two triangles are congruent, so from CPCT I'll say that AP is equal to AQ, right? So write down whatever is given. So first it is given that AP and AQ are two tangents. Right? From point A to the circle. This is given. Okay, now to prove, you have to prove that AP is equal to AQ. So basically this is the construction that join, which I've done from the dotted lines, that you join OP, OQ and AO. Now proof. So let us try to prove that the two triangles are congruent, right? AOP and AOQ. So I need three things. So first I can see that OA is common, right? Okay, what else do I have? So the next thing I can have is that this angle is 90 degree, isn't it? From the theorem. Yes. What is the third thing I can have here? Come on. See, Harsha, when you are trying to show congruency, right? So first you look at the sides and then you look at the angles. That's it. Okay? Please unmute yourself. Yes, Harsha, can you hear me? Harsha, can you hear me?
Ma'am, my screen was hanging, sorry.
Okay. So first of all, let us say this angle is 90 degree from the theorem. Okay, then I'll show congruency. So since tangent at any point of a circle is perpendicular to the radius through the point of contact. I mean, this is a theorem which I'm using.